Welcome to all of you. This is Umang Mishra from Bennett University. I welcome all of you to this seminar on the topic of SONET, or synchronous optical networking. The agenda today, or the topics to cover today are basics of SONET, of course, the SONET devices, the structure of SONET, the operations that we will do on SONET, a frame of SONET, a network situation of SONET, and of course the applications of SONET. What is SONET really? First of all, SONET stands for Synchronous Optical Networking. It was first proposed by Belco Laboratories in 1980 and it is an optical transmission interface. The term optical transmission interface means the data transfers itself into a digital medium through optic fibers through this method. SONET is of course a time division multiplexer. That means the time is synchronous here. Now, for the first topic, our topic is basics of SONET. The points that are covered through this are what is SONET, what are the design goals of SONET, and variations. Let's go. Now, the design goals of SONET. Now, SONET being a synchronous network requires a single clock to handle timing synchronization and equipment across the network. The real meaning behind this is a single clock handles all the mathematical abbreviations required here to maintain the 0 and 1 frequency traveling through the fiber. The physical specification frame design must include mechanism that will allow it to carry signals from incompatible tributary systems. That means the various tributary systems or the lesser known systems should have the capability to allow an add mux to simplify the design and transfer the data required to a regenerator or else. More points will be discussed after this. Given here is saying that SONET is a multiplex transfer mechanism and hence can be the carrier of broadband services at ATM and BISDN. We all know what ATM is. For BISDN, it's a broadband internet service domain networking. Now, SONET devices. The SONET technology function itself on three main devices. These are as follows: synchronous transport signal, or in short STS multiplexers. These multiplexers are synchronous with respect to time, i.e. this means that the time in each frame remains constant. It revolves around the same frequency. That means each data center or a data frame will have the same amount of time packets required to transfer it from one place to another. That means each data frame has the only same amount of data required to transfer from A to B. Regenerators. Of course, at itself the term is itself mentioning, it is used to increase the transmitting distance between two sender and receiver. How it does? It copies the regenerating signal provided by the STS mask and regenerates on the same frequency. That relates itself that there will be no noise or no interference available between selected points. Hence, regenerator can be accessed to increase the transmission distance, but we have to be careful about the loss function it generates. You cannot add too many regenerators and fail to achieve a transmission percentage high. Now, add drop multiplexers. Between a point of receiver and sender, there will be unwanted signals too, and there may be important signals that need to come from distributed services. Hence, the add drop multiplexer is used to increase or decrease the optical fiber input required in a section. Now let's see here. This is a basic SONET structure. It contains some terminals and STS mux, demux that I discussed earlier, a regenerator, again an add and drop mux, a regenerator again, and the final receiver end, that is STS mux and demux, and the other terminals that will receive the output. You can see it as if any way you like. You can go from left to right or right to left on your choice. Let's see here. If you want to have an overview of a SONET structure defined here, it can say that the base module displayed here consists of the devices we have discussed before. The three main devices that were discussed before are shown here. Let's say either the sender send or the receiver send, the transmit terminals can either be defined there. Let's say they serve as an input and the output ends up transmitting data. The STS mux and demux serves as an initiator for the SONET by either multiplying or demultiplexing the data stream. What does this mean? This means that the input is either reducing or increasing or distributing itself on various streams as per the required use. The regenerator then that we discussed thoroughly is generally used to increase the transmission data, and considering the loss variation, you can apply as much as the regenerator as you want to increase the transmission data. The add drop mux situation we have already discussed, but it of course allows us to introduce more optical fiber transmission between the transmitted data. What are the operations that are happening in SONET is the main thing that we need to discuss here. The structure has been discussed, but the functionalities and each of these devices or each of the transmission point go through is what we really need to know. The structure has been discussed. Now let's see. The STS multiplexer demultiplexer, of course, is used for two purposes. It multiplexes various signals from various sources, of course, that I told you, into an STS signal. Is a synchronous transport signal where time is synchronous, or it demultiplexes an STS signal in that output section into various destination signals. Excuse me. The STS signal passes through a number of regenerators or repeaters by traveling from source to source destination. This means that the amount of regenerator you require to increase the transmission line distance can be thoroughly used by you, considering the loss variance you will incur by increasing the regenerator data. The regenerators, of course, are bidirectional as they need to be because you can easily switch the input and output in this SONET device. They are used to regenerate the STS signal applied to them. This, of course, results in an additive noise that will reduce the quality of transmission. The regenerators function on the data link layer. Any operation between the regeneration, either the amplitude increasing or it remains same, it will happen at the data link layer. The layer is untouched. This helps us in reducing the noise output. The add drop multiplexer has one main use. In my case, or in anyone's case, the main use of an add drop mux is to introduce additional signals from various sources. This may mean that you have some kind of interference data that may be required in output decisions. So we need to introduce it between this network section. It can also remove unwanted or restrictive signals that are not required in your section. One more point for add drop mux is that it can direct the demultiplexing. That means the either multiplexed server can be redirected and vice versa, of course. The base meaning behind this term is that the add drop mux can be used as a reversible coin. If you want to multiply something or multiplex something, you can use it. If you want to decrease something, you can of course use it. It's on your own prestige what you want to do with an add drop mux. Now let's go on to an important topic that I think is in SONET. We have discussed the structure of SONET and we have now a basic overview and what the SONET actually does. But the data frame of SONET, a single frame we will discuss here in this topic. It's an important topic, so let's focus ourselves. Here we see a SONET frame. It's a simple example of SONET frame. Some details are missing that I will discuss thoroughly in the next slide. Let's say here something. Now let's see. If we take a cursor here, we see this is the information payload and this is the transport overhead. These two are the basic sections of any SONET frame. As we can see, an entire row is shown to be 90 bytes. The three first bytes are reserved for the transport overhead and the other 87 bytes are reserved for the information payload. Keep this in mind, this is a simple section, so it cannot show 9 rows here. But you do realize that each row contains 90 bits, not 9 rows containing 90 bits. That means each row is containing 90 bits. So the 9 rows will contain, of course, 9 into 90 bits. That is 810 bits. Let's move on, shall we? If we want to have an overview of a SONET frame, let's go step by step. Here we show as a simple view of a frame. If each frame contains 9 rows and each row has a size of 90 bytes, the first 3 rows of each individual row, that means every consecutive row has 3 bytes reserved for the transport overhead. That means the data center information payload, of course, the size will be 87 bytes for each row. That means that the total space available for each frame to transmit data equals to 783 bytes. That is the amount of information you can send in a single frame of a SONET structure. Sorry. Overview of a SONET frame. Let's see. We saw the transport section contains 3 bytes. If there are 9 rows, of course, it will contain 27 bytes of data. As shown in that image, the transport, or of course as is called an administrative overhead, is further divided into 2 sections. The 2 sections are namely a section overhead and a line overhead. Let's first discuss the section overhead. Of course, the section overhead occupies 3 rows with 3 bytes available to each row. This will result in a total storage capacity of 9 bytes. The main functionality of the section overhead is what we are interested in here. It does the framing, error monitoring, and management function. So the section overhead has 3 main data qualities that are required for a processing of a good network system. The line overhead acquires the remaining 6 rows. Hence, it contains a space of 18 bytes. It tells the synchronization, or it handles the synchronization of the system. It handles the multiplexing and demultiplexing of the system, and it also handles the personal switching or the protection switching of the system. It means all the security related systems or all the changes and variables of a system in the synchronous time as handled by the line overhead. Each frame period amounts in 125 microseconds. This means that if we want to calculate the data rate of each frame, it will equal to 50.122 Mbps. That is the data rate of each frame in a SONET network. This is much clearer. Now let's go. Topic 3 is a SONET network system. Before introducing SONET networking, let's first cover up what have we learned till now. We learned that the structure of SONET behaves, how the devices that are required to perform a simple SONET network we discussed. We also discussed a single frame of a SONET network and what are the data capabilities and transmission rate of that network. The data rate, of course, we realize is to be 50.122 Mbps of each data frame. In networking, we will look at a different feature of a SONET networking, and we need to be clear that what it means and how it helps in a daily system. Let's introduce the SONET networking. A SONET networker. This is a basic model of a SONET network. It is also called a SONET ring. As you can see, this is a ring. So a simple ring is there. Looking at it firsthand, you cannot seem to understand what is really happening here. The ADM or DC, as I mentioned here, is an add drop multiplexer. That much is clear. Now we see there's a working line and a standby line, and there's a working line and another standby line again. From this we can infer that there are 2 sections of work going around here. There either a clockwise section of working and a standby line, and there's an anti-clockwise section of working and standby line, signified by red and blue color exclusive. Let's move forward. If you want to have an overview of this diagram, this is a basic model for SONET. The red and blue communication lines, as I discussed earlier, represent the clockwise and the anti-clockwise direction in which this network is heading. The standby section here are the most important thing, and that will be discussed later in this slide. First of all, let's be clear. This is an add-drop section networking of a topological circuit between 4 sections. No need to be confused there. This is a simple circuit. It can be as many circuits as you want. This is a basic example of four circuit system. Let's move on. How the SONET ring works. The ring that I showed here. How does it work? The SONET ring works as the diagram as was shown there. The SONET ring was the outer rings, that rings that I mentioned to be working. Red or blue, either way, either direction, are called the working rings. These dignify that the main lines that the data is transmitting over through the ATMs between each circuit. That means the working line are the main line that the try to transmit through. The inner ring is what we are focused on. The inner ring is also called a protection ring. This term may be introduced as a ring because it is used to dignify something or to help the data transmission if either a working line disturbs itself or there's a failure occurring between two circuit points. Hence, even if a working line fails, a protection ring can still protect the data and transmit it through the same data frame speed. Now, various network models has been based on this SONET. The model that I showed you was a simple bidirectional failsafe network, and it calculates the protection ring on both the senders and the receiver's end. What the term the protection between both the senders and receiver end means, the sender itself can be the receiver at some time and the receiver's end itself can be the sender. We introduced this product as an add drop mux as I mentioned in this first slide. Now let's go forward. What are the applications of SONET? Here it's showing that SONET can be used as a carrier for ISDN and BISDN networks. What are these? Let me introduce it to you. Now, ISDN network is an internet data networking system. The term itself means it's a broadband system through into a LAN. So there's not a high requirement of carrying data at higher speeds. That means the data can be transmitted at T1 speed. SONET can be used as a carrier for ATM cells. Yes, this is true. As the process is synchronous, that means ATM need to work on the same time. The SONET can be used as a synchronous system to handle any ATM calls. On-demand bandwidth is a current problem that is occurring in the system networking. So SONET can be used to resolve that problem too. Although not in pure use, the SONET is also used as a cable network for TV and various satellite dishes. Nowadays, the cable system has gone haywire, so I guess SONET has lost is used in that TV section. Although the transmission data still happens, it may not be as fluent and required as much as was required previously. Of course, the main use of SONET is in T1 and T3 carrier lines. The T1 and T3 carrier lines represent the amount of speed a data frame can pass through in some seconds. The T3, as I remember, represent a speed of 44 Mbps, as much as 44 Mbps going through. Now, as far as we have come on this slide and this seminar, let's have a simple flow chart to summarize ourselves in what we have discussed earlier. If we see the 5 points clearly, this is simply a standard set of SONET devices interacting with each other to transfer data from one STS bus to the other STS bus. Of course, if you want to focus on each of the bullet points mentioned here, you realize that it is what we have discussed, that the input frame is transmitted to the STS bus. The regenerator, of course, regenerates or reframes the data to increase the range. The add drop mux, of course, such as we have discussed. The final wave, of course, can be regenerated again. This is a simple example. There's no need to have two regenerators or have any regenerator itself. The regenerators are your compatible partners. If you want to increase the transmission line, you use a the final STS signal is received and redirected to various sections as required. That is the STS receiver mux. Now, listen clearly. The order can be reversed. The STS receiver can become the sender, but that is based on your situation requirement. There's no need to focus on the direction that is required. Just focus on the process. The step-by-step process of how a SONET system works is all the requirement that you need to process yourself a new SONET networking system. Now that I have completed a basic overview, let's say a basic overview on SONET technology, let's look into a hybrid form of a SONET technology that is now popular. It's called an SDH technology. SDH technology, or synchronous digital hierarchy, in short, is a transmission interface that transfers multiple bit streams synchronously over optical fibers. Seems like the SONET and SDH are same. They are same but not itself. The difference becomes in the framework. I will discuss it afterwards. Of course, SDH is a hybrid form of SONET and PDH. PDF itself is a predecessor of SDH, and the disadvantages that happened with PDH are resolved by this version of SDH. It is also a time division multiplexing system. That means the time itself is synchronous here. That means a single clock system is based here. The standardized section here is handled by International Telecommunication Union, or ITO in short. If we want to look into a signal hierarchy that the SDH produced, it will be that the basic rate is 155.2 Mbps, which is called an STM1. There are various STMs, STM1, STM4, STM16, STM32. The thing discussed here is STM1. That means synchronous transport module level 1. There are various levels that define the various data frame speeds on which a network works. If we consider the STM section of level 1, we see that there are 270 columns. In SONET, there are only how many? There were only 9 rows. Yes, the difference here is the size of data frame available here. The SONET itself is a small data frame, but SDH has a higher data frame quality and quantity. Hence, the signal hierarchy is higher in SDH. The transmission speed may be seen, that is 125 microseconds, but the frame itself are 8000 in this fiber optic circuit. If an STM frame contains 9 rows and 270 columns as shown in that image, then the total number of byte transfer will be 2, 3 and 40, 2340 bytes. The amount we received in that SONET system was, there were 9 rows, hence the total number of byte will be 81. Yes, the difference here is starkly. Instead of a traditional separation of administrative block as in SONET, of course there were 2 separations in SONET. Here there are 3 separations: an RSO section, an AUP section, and an MSO section. The RSO section has 3 rows, which results in the total space required to be 27 bytes. AUP is an identifier section. It requires 0 or 1, hence it only requires a single byte. An MSO system has a 5 byte system, and the total space required will be 5 cross 9, that will be 45 bytes. The section frame has been solved here by the STM SDH. So we now know that the SONET and SDH are similar and yet different based on their frame size and transmission pipe. These are the few references that I used to develop this PPT, and this video cannot be finished without differencing them. Thank you. Again, my name is Mang Mishra. This is my official email address. If any customization or anything you require, you need to mention to me, you can contact me this email ID. I would like to specially mention Dr. Gagandeep Kaur for this seminar. And thank you. Have a good day. Cheers.